Hey everyone, welcome to Unit 7's other FRQ. It is 2014's problem number 7. This is a little baby question, so all of the questions on the smaller ones are related kind of to the same content, so it's not surprising that this is all kinetics all the time. If we look at number 7, it says the half-life of the catalyzed isomerization of cis-2-butene gas to produce trans-2-butene gas represented above was measured under various conditions. Now, when you look at this, you say to yourself, holy crap, I have no idea, A, what isomerization means, maybe, and what is this cis-2-butene and trans-2-butene? I'm not really sure. They tell you these pictures appear at the top. Honestly, they're not super important. Don't let all of this crazy stuff freak you out, because at the end of the day, it is just a kinetics problem. Now you say to yourself, that's great, Mrs. Audemire. You saw the problem. How do you know? I can tell you that they put in a lot of terms there, but if you have the chemistry knowledge, you are going to be able to figure it out, even though there's a ton of gobbledygook here at the top, okay? So don't freak out. If we look, we have 4 trials. We have the initial pressure of our things, and if you look here, we have all of these are the same pressure except for the second equation, or the second trial. Different volumes, same temperatures except for the last one, and then some half-lives here. So we've got a half-life. So it says the reaction is first order. Explain how the data in the table are consistent with a first order reaction. So if you look at the different trials here, the big tip-off for the hand here is that the half-life is consistent for those trials that are at the same temperature. First-order reactions have a constant half-life. I have seen a question relating to this type of stuff every year since they redesigned the test. So really, really make sure that you know this stuff. So that is what I'm going to write. The reactions, or the reaction trials, have a consistent half-life at the same temp. Sorry, I keep screwing up here. It's hard to write and talk at the same time. First order reactions have a constant half-life. And that's it. Boom, done. Let's say constant half-life at constant T. And then we're good to go. All right, moving on to B. It says calculate the rate constant K for the reaction at 350. Include appropriate units for your answer. Like I said, I've had tons of questions about first order having a constant rate. The other thing I see is using the K equation for half-life. On your equation sheet, you should have that T half is equal to 0.693 over K. So if I want to figure out what my K value is, I'm going to switch these guys up and have it so that K is equal to 0.693 divided by T half. And I know that my half-life from the previous part of the problem, that data table up here, tells me it's 100 seconds. So what I'm going to do is I'm going to take 0.693 divided by 100 seconds, and I'm going to get a half-life of 0.00693, and then the units on this are going to be seconds to the -1, or you could leave them as 1 over seconds, and both would be fine. So all you're going to do is take 0.693 and divide it by 100. Know these two parts. These should really be on your one sheet or somewhere, because they always ask a question like this. All right, moving on to C. Is the initial rate of the reaction in trial 1 greater than or less than or equal to the rate in trial 2? Justify your answer. All right, so if we look at the data table here, the difference between trial number 1 is the pressure of the cis-2-butene here. So if I look at the pressures, trial 2 has more pressure, which means that there's more chemical floating around in there than trial 2. And so you know that if there is more reactant, the rate is going to be faster. So what we've got to do is we go back here. I would say because the rate depends on the concentration of the cis 2-butene, because trial 1 has a lower pressure, there are fewer reactants than in trial 2. And then I would maybe make a little note that has same V and T just to cover my butt, okay? So again, because the rate depends on the concentration of the cis-2-butene, because trial 1 has a lower pressure, there are fewer reactants. This makes the rate of trial 1 slower than trial 2. And that's it. So it hopefully makes sense to you because I have less stuff in my reactants. I have twice the pressure, but the other things are consistent. I am going to have more reactant in my second trial, and therefore my reaction is going to go faster. All right. I'm going to come back up here because I know that it's asking about the data table for this last one. So for 7D, it says the half-life of the reaction in trial 4 is less than the half-life of the trial and reaction of trial 1. Explain why in terms of activation energy. So they're kind of tipping their hand to you already that something is better about the activation energy in the second one that's making its half-life a little bit faster. And if we look here, we've got a temperature of 365 Kelvin versus 350. So what we need to do is talk about that. So what I'm going to say is that the fourth trial occurs at a higher temp than trial 3. Or trial 1, whatever it's asking about. Okay. This means the molecules in trial 4 have a higher kinetic energy than trial 1. If molecules have higher kinetic energy, they are more likely to reach activation energy and will react faster. And I think that's all you probably need for that one. Or you have, more likely to reach activation energy, and maybe not reach, but reach and overcome. Because if you think about activation energy, so if you think about our reaction mechanism, like this, it's okay if it reaches it. Lots of things can reach it. The trick is that not only do we have to reach it, we have to overcome it to come down the hill here to get to the product side. So that might be a little bit wording that you have to be careful with there. All right. Hopefully that clears things up. If you have any questions, come ask in a meet.